Thanks for the intro. Hi, everyone. My name is Aditya. I'm a PhD student at NYU, New York University. And yeah, I didn't start off in Git. I started more in the software supply chain security space. I've been working on how we can trust the software we produce for various aspects of it for quite a while. And a couple years ago, I found my way to focusing on source code integrity in particular. As part of all of this, I'm involved in various projects like, well, Gittuf that I'm going to talk about now, but also the in-toto framework, as well as I'm a contributor to the update framework and so on and so forth. So supply chain security, right? How can we trust the software we produce? Like, there's been a lot of work in the last couple of years, especially with like, hey, we got to secure our build systems. We got to know how our software is built, so on and so forth. But a relatively lesser focus on the source code part of it. And of course, the source code is the universal starting point for all of our software, and usually managed using version control systems. And so, that was my journey to thinking about, hey, how can we improve source code integrity using something like Git? So the first threat here really is someone, maybe it's a malicious insider, someone gets compromised, they make a change that they're not supposed to, and generally speaking, the recommendation is, hey, why don't we get like multiple people to review your code before it gets in, and basically ensure that a single person can't just push a bunch of code to like your main branch or something, and try and mitigate this malicious insider attack vector. But the thing here is, like, this is usually enforced using something like your source control platform, your Git server, whatever. You switch on some controls saying, hey, I have branch protection rules, or I have minimum approval requirements, etc. But that works really well. I use it myself, but it does mean that there's a single point of trust in this entire system. And it's not always perhaps the case that we can rely on the single point of trust. I'm also like thinking of cases in like enterprise environments or so on, like where Git servers have been hacked before. And like we've seen this with the PHP project. I think that's like the most famous example in my mind, where someone was able to like bypass the server security controls and push commits directly to the repository. But also just going back to that case of like rogue insiders, if you got a self-hosted SCP at your organization, right? The rogue insiders may be the people operating, potentially, your source control platform in-house. So the solution that we started thinking about was, how can we make it so we can enforce and independently verify these kinds of security policies? And like that was our goal, and it has a couple of implications there. On the one hand, it also means like the folks who are responsible for running your source control platform, they're not like solely responsible for keeping that platform secure and actually functioning correctly and enforcing your security controls. And it also allows you to do all kinds of other neat things, like, hey, when I check out my repository and I'm going to build from it in my CI system, I'm actually going to go verify my policies again before I actually build it. I'm not just going to say, hey, this thing that the server gave me is perfectly right, like everything that was supposed to be merged in was merged in correctly, so on and so forth. So yeah. And the building blocks we identified to achieving all of this is we need a verifiable way to authenticate developers. We need a log of repository activity, what's happening, who's making what changes. And we need some verifiable representation of repository policy, some way for the owners of a repository to say, this is the policy for my repository, right? And so if you map that back to existing Git features, we have a verifiable way of authenticating developers, cryptographic signatures, though as Scott showed right before I got started, they're not as used as they perhaps should be. But it's nice that we get that out of the box, right? The log of repository activity, not quite there. And it's also like, definitely not the Git log. It's closer to your Git ref log because you want to know how your references evolved over time. And the repository policy as well, Git itself is not very opinionated. It tries to be agnostic of how you do security controls for your repository. And even just, it doesn't even take on the burden of key management for the cryptographic signing it supports out of the box, right? So it's agnostic. So zooming in a bit more, as I hinted at just a moment ago, repository activity is, hey, who pushed what to which part of the repository? So that's like the baseline level of information we want. And we also want this log of activity to be tamper evident in and of itself. We don't want someone to go in and say, hey, I'm going to reorder events as they happened, or I'm going to just drop this push that happened. You want to be able to recognize that someone tampered with it if someone did tamper with it. The policy, again, by definition, a declaration of who can write to which part of your repository. For example, Alice and Bob can make changes to the main branch. And you also want to version your policies, because security policies change over time. People join your team, or people leave the project. Happens all the time, or someone needs to rotate their keys. So we need to know how policies evolve as well. And at this point, we were like, okay, all of this is really just a content tracking problem, and we have a pretty good content tracker. So how do we just use Git, store a bunch of extra content to represent all of this to secure your Git repository, right? So like I said, the signatures answers the who part. We're going to store additional metadata about the what and which part of the repository was pushed to part. And for the tamper evident part, aspect of the activity log, we can reuse Git's Merkle graph capabilities that are already used for the commit graph, right? So the policy, again, additional authenticated metadata, and versioned, again, we have a perfectly capable content tracker here, which automatically tells us how objects in our repository evolve over time. And that's Gittuf. So like a lot of projects that have been discussed in over the day today, we make use of the special references. We got dangling branches in there. So we got something we call the reference state log, which is an authenticated record of who's pushing what to which branch. Each record in that is basically just a commit that's signed and contains the information about what changed. The policy is again stored in a separate reference, and each entry contains the full set of metadata, the policy metadata available at that point in time. And the policy reference is in itself tracked by the RSL, so that again, when the policy was pushed to, when it changed, in context with all your other branches in the repository. So yeah, super quick diagram, I guess. Sorry, I'm partially an academic. I figure, yes, there we go. So that's roughly what it looks like. You got an append-only list of entries. You got your policy, then maybe a push to your feature branch, main branch, etc. The Gittuf policy is inspired by the update framework, which I highlighted at the start as another project I contribute to. Again, I don't know if folks here are familiar with it, but the update framework, or TUF, started off as a way to securely distribute artifacts, especially with a focus on packaging ecosystems and so on and so forth. It's since kind of been generalized and used for a bunch of other related software distribution problems, and to bootstrap roots of trust and so on and so forth. So we use TUF semantics to get our root of trust, because as I pointed out, we have signed policy metadata, and we need a reason to trust that signed policy metadata. So we use TUF for that, to kind of bootstrap the root of trust. TUF also has this notion of delegations, which are basically the ability to grant trust to another party for some particular namespace, which is, again, very similar to what we want to do with the rules about who can write to which part of our Git repository, right? And finally, again, TUF supports something called thresholds, which is the minimum number of required signatures for that particular delegation or rule. So here's a somewhat truncated snippet of a Gittuf rule. It doesn't actually look like this. I've cleaned it up so that it'll fit better on the slides. But basically what this rule says is it's going to protect the main branch, and it's going to say that only the holder of that GPG key can write to the main branch. We also support SSH keys and rules over file paths. And my co-maintainer, who was listed on the stock but couldn't fly out, he is one of the maintainers of Gitsign, and if folks aren't familiar with the Sigstore project more broadly, it is a project that makes it easier to create cryptographic signatures without having to take on the burden of managing long-lived keys, because it uses OIDC to authenticate you in that moment of time and kind of grant power for an ephemeral key that's then thrown away, et cetera. So it's a pretty neat system. So if folks haven't already encountered it and have key management woes, you should go check that out as well. But yeah, we also support Gitsign, which is the Sigstore tool for signing Git commits. You could also say, so instead of specifying an SSH key or GPG key, you can also just say, hey, these tags, the version tags, must be signed using my signing identity, which is my email ID, and the OIDC provider here we trust is GitHub. So the tooling is mainly the GitHub CLI that you use to manage your policy, et cetera. And we've also written a Git remote helper that, because overwhelmingly the operations that need to be performed by developers here are, hey, you need to record some additional metadata during a push, and you need to fetch some additional metadata from the server during a fetch. So we've also written that, though that one's really more of a work in progress. Yeah, it's been a relatively recent addition to the repository. So in action, we've got, let's say, a copy of a local repository. We're using Gittuf. We can see the RSL. We can see the policy reference. I make a change to the main branch. And when it's time for me to push to the Git server, the transport or whatever I'm using to create that RSL entry, so adds that record of the push to the corresponding reference, signed using, again, my signing key. The server could, if it supports it, it could optionally verify that the push to the main branch is allowed according to the current policy. But even if not, any other Gittuf client, when they fetch it down, they get both of those entries, and then they can independently verify that everything's fine. And if you have Git-only people fetching from the repository, well, I guess they just only get that main branch commit because they're unaware that the RSL exists, the policy exists, so on and so forth. I mentioned thresholds a moment earlier, and you didn't really see any hint of that in the previous quick in-action part, but you sometimes do have rules, like we want all of our changes to this particular branch be approved by at least 2 people, things like that. And that's where we, again, want to store additional metadata about such approval actions. And we use the in-toto framework that I'm also a maintainer of for that. So the in-toto attestations are authenticated statements used in the software supply chain space about how software is produced. So we store these attestations again in another special reference. And this is also recorded in the RSL so that you know that the approval happened before that thing was actually merged into the main branch or so on. So that's roughly, that's actually all of the attestation that we're recording for an approval at the moment. It's kind of like a work in progress. You see it's tagged with a v0.1. We're hoping to stabilize it in conjunction with a few other projects. But all it really says is the branch that's being updated is here the master branch, and it says I'm approving it in the context of where the master branch currently is and what the pre-computed tree ID of where it's going to be after this merge happens, because we can't, of course, compute the merge commit ahead of time. So we just expect them to be tree same. And then this gets signed and stored in the attestations ref. Just a brief tangent. There are other interesting uses of attestations in this namespace, because you could also plug in questions in your policy like, hey, did my change also get tested in CI? Did my CI system issue an attestation saying it tested that particular revision and everything passed? It really allows for a lot of extensibility, and I'm really excited about where we can go with that. We could also build in verification summaries. Maybe it's really expensive for every system everywhere in this setup to verify the policy all the time. So you still have multiple verifiers, but they issue a verification summary saying, hey, we verified it, and you can be like, hey, did I get 3 verification summaries from verifiers I trust so that I don't have to verify it myself, and so on. So finally, there's a project called Salsa in the Linux Foundation, part of the Open Source Security Foundation, that is, you could think of it as like a semi-gamified with multiple levels set of requirements for how to improve the posture of your software supply chain. in-toto is already part of that. It's so far Salsa frameworks, the release parts have focused on build pipelines, but there's ongoing work for source-specific attestations and requirements. And yeah, with that, I'm going to switch over super quickly to a demo, which I decidedly do not want to type out live, so I've just got it up on ASCII-Cinema. I'm never quite sure how to say that. So first off, you can see that I've got like an SSH server running for this for the demo. And I'm going to clone a repository on that server using the Gittuf remote helper so that when I go into the repository, I have like a couple commits in my main branch, but you can also see that the remote helper ensured that the RSL was fetched down and everything. And again, each of those entries are individually signed, and they basically just tell you, where the last push was, and that this one says the main branch is set to that particular commit ID. So we can also take a quick look at the policy ref. We see there have been some policies. If we list them, we'll see that there is a rule that protects the main branch with, we need 2 signatures from those specific SSH keys. So we can verify at this point, having just cloned it, that everything it looks good, and it does. So let's make a change. And again, for the demo, I've already set my signing key to be Alice's signing key, one of 2 keys that we're going to use in the demo. And I'm going to check out a new branch. I'm going to eventually get around to adding something. There we go. The world. Add that, commit that. And push, at which point the transport again adds that notion to the RSL. So at this point, we need 2 signatures to merge something into the main branch. So I didn't bother switching different terminal windows or something. I'm going to pretend I'm now Bob, and I'm going to create that attestation, right, that approves this particular change from to land in the main branch. So Bob's going to say it's coming from that branch, and this is where I explicitly set Bob's key instead. And I say the target of this is the main branch. And you can see that that added something to the RSL as well. Just sync stuff up, going back to being Alice. There we go. Check out the main branch. Alice can merge it. Alice pushes it, and Alice's signature is attached automatically again with the RSL log entry, the RSL entry, which gives us the 2 signatures we need for this particular policy. So if we verify now, everything looks good. If Alice, for example, were to try and make a change unilaterally, doesn't want to say hello to the world, just put it in, commit that. Push, there we go. I realize I typed slower than I thought, but anyway. We try to verify it this time, it fails. So you can also see, again, that if we were to clone this repository from the server again, and say we're a CI system or something, and we wanted to verify it ourselves, verification would fail again. With that, super quick. Cool. So just going to wind up. I'm almost out of time. Right. So this significantly also improves the auditability of how policies change, what policy applies to a particular prior revision of your repository and all of that. A lot of these features perhaps make more sense for like larger repositories or teams where you have this kind of internal hierarchy. And I really want to like point out that owners of a repository continue to be trusted, so this isn't really like a solution for something like the XZ incident from a few months ago, where like the maintainer themselves basically try to backdoor the package, right? Well, long story, but yeah. We want to make more improvements to all of this. We want to improve the Git remote Gittuf transport, and we are also like looking at integrations with SCP and review tools, because it would be really nice if we could get a lot of this kind of metadata while people can still continue to use like GitHub's pull request approval mechanism and so on. We can't expect people, to start typing approvals in their terminal all the time. It changes the trust model a little bit, but there's a balance of usability and security at play here. So those are the stuff we want to do next. And we have an active community. Come say hello. We're part of the OpenSSF in the Linux Foundation. We're a sandbox project there. We got a Slack channel. We've got a mailing list, and everything we do is built on that GitHub org. So thanks. Oh yeah, last thing. I put up a proposal for unconference talk to talk about this and generally software supply chain security and source code integrity. If you're interested, come say hello tomorrow.